How about we give one of these a shot by hand? What do you say? Your enthusiasm is just overwhelming. All right. So right at the end of your lesson 7, you'll see a practice problem here that we'll go through together. So what I would like to do is go through this once working together, and then give you another design flow, and then you go through that, and I'll walk around and answer questions and help out, and then we'll review it together as everyone finishes off. Okay? So read off of your sheets. You don't need to necessarily look at the screen for this, because we tried to size the screen so you can see, but then I can't fit everything on there all at once, so that's okay. So we have a culvert crossing must be designed for a new roadway, and the site survey project contains all kinds of goodies for us. Okay? So we actually have a schematic. We're giving the overtopping roadway elevation of 256 feet. So we can say that our allowable can be no greater than 256, and we may even want to set it below that. Right? If we don't want roadway overtopping for our design flow, then our allowable can be no larger than 256. For sake of simplicity, we'll just say it's 256 feet. So that's our do not exceed. The allowable headwater elevation is our do not exceed level. So if we calculate a headwater, controlling headwater from our calculations, and it's greater than 256, we know we have to go back and try a different culvert size, shape, whatever, maybe material. Culvert length is 149 feet. The culvert slope is 0.005 feet per foot. And we're also given the inlet elevation and the outlet elevations, right? Site visit notes. There's no significant debris potential. If we actually were working in the site and there's potential for a lot of tree limbs and sediment washing in there and whatnot, we may want to be conservative and make our culvert a bit larger, acknowledging the fact that the capacity could be diminished if we start having some trees and things deposited at the inlet of our culvert. The design so no nearby structures either. Design criteria for this project, the 50-year frequency, which is pretty common for culverts on interstates. Allowable headwater, the allowable headwater elevation is actually less than the overtopping, so it's 253 feet. So disregard what I said before, 253 feet due to the elevation of a different roadway upstream of the subject culvert. You see a 100-year frequency for check. So in hydraulic design, what we usually do is we have a design flow that we use to initially size our structure, and then we typically choose a check flood, which is the vast majority of times larger than our design flow, and it's the what-if scenario. We're designing for a 50-year event, but what if the 100-year event occurs? What's going to happen? If it washes out the roadway, you may want to take that into consideration and make your culvert larger. Okay? Rational method that Veronica covered, and which is pretty typical for your small drainage areas, was used to determine the following values in a flood frequency curve. So it's given that your 50-year event is 93 cubic feet per second, and your check flood, your Q100, is 125 feet per second. You're given another goodie here. You see this is your rating curve. A typical tailwater section representing the downstream channel is trapezoidal. It has an 8-foot bottom width and 1-to-1 side slopes, and the bed slope is still 0.005. The estimated Manning's end roughness value is 0.045, and based on that, a rating curve was developed by normal depth analysis. So how did they determine this rating curve? What equation did they use? Normal depth? They assumed steady uniform flow conditions. They used Manning's equation. And what they did was they just guessed at some various depths and then calculated the discharge, and they made this rating curve. Given that we have computer software nowadays, you can just generate a rating curve yourself. You just specify a minimum flow, maximum flow. In HY8 or the hydraulic toolbox, it will just generate, it will solve Manning's equation for all the different discharges in between, and it will generate this for you. Or it will just do the calculation directly. Okay, so rating curves, for the most part, are pretty much done automatically by software anymore. We don't need to do these by hand. Okay, so we see that for our 93 CFS, or design flow, we're given a tailwater depth of 2.57 feet, and the velocity at that flow depth is the average velocity is 3.4 feet per second. And we're given the maximum average stream velocity for 125 CFS is 3.7 feet per second. So given all that good information, they say, well, try a double 36-inch corrugated steel pipe solution and see if that's going to be sufficient for your culvert crossing. And we're using a square-edged entrance. So the first part is a little bit tedious. We have to plug in. You should have this sheet here. It looks like this worksheet. And we now have to plug in all of our given information in here. There should actually be a culvert diagram right here. See worksheets, yeah. So actually your worksheet, the one that you can get out of HDS5 should have a culvert diagram here, and then you can just label all of the different elevations in it. So this will be a little bit tedious, but you do have that on the given information on page 2. So it's just a matter of translating the figure on page 2 into here. Not a big deal. Sorry about that.
That one does have extra information that's not on this one specifically.
Well, this is the solution.
Oh, okay.
Yeah, so I know if we're on the right track.
Okay.
All right, so we'll actually, that's okay. If you wanted to, what you could do is, you could do in that empty square there, if you really wanted to, you could do a quick sketch of this. And then put in all this information again, you know, the inlet and outlet, the 253, which is your allowable headwater elevation. And I think those are the key pieces of information. And while you're doing that, I will start writing in the other information we need in our worksheets. The hydrologic data, we're using the rational method. We're given a stream slope of 0.005, so 10% feet per foot. Our channel shape is trapezoidal. The first flow we're looking at is our 50-year, our recurrence interval 50-year, and the flow for that was 93 CFS. And we go back to that rating curve, that Manning's rating curve, and we see for 93 cubic feet per second, the tailwater depth is 2.57 feet. So that's just a solution of Manning's equation for that trapezoidal channel for a flow of 93 CFS. We're also, after we solve the 50-year event, we're going to look at the 100-year event. You're going to do that on your own. And that flow is 125 CFS. And the tailwater depth from our rating curve for that flow is 3.04 feet. anytime here, if you need me to repeat something or go back over something, or if I move the chart where you can't see a number, just give a yell out and I'll make an adjustment. We're going to try a double 36-inch by, the length was given as 149 feet. CSP, that's corrugated steel pipe, square-edged head wall. That should actually be the road level, so I've already made a loop. It's just right here. Yeah, if you duplicate exactly what I'm doing, then you'll probably be making mistakes. That's just who I am. I embrace myself the way I was made, and I make mistakes. The total flow is 93 CFS. And here's the thing. When we go to our design charts to do the solutions, for multiple pipes, it's the flow per barrel that we use as the cue when we enter the chart. If we solve it for a box culvert, it's the flow per foot of width. So we have to divide the flow by the span or the width of the culvert. If it's a double box culvert, then it's the flow per width per barrel. So we have to divide by the barrel, the number of barrels, and also then the width of the barrel. So it's basically comes down to the flow per foot of your conveyance span. Right? Does that make sense? So when we're actually looking at two corrugated steel pipes, the flow per barrel is that 93 divided by 2, which is 46.5 CFS per barrel. So you see the next column over, it says, well, HW sub I with subscript I is the headwater from the inlet control solution. So we need to check the inlet control headwater, calculate the outlet control headwater, compare those two. We're going to take the one with the highest headwater because we're going to assume the minimum performance, and then compare that to the allowable. So HW sub I is the headwater based on inlet control. So we get that using our fancy schmancy design nomographs. Okay? So you're going to see some different charts in your packet there. And the one we're going to look at first is chart 2B. You see in the upper right-hand corner of chart 2B a circle, which means it's for pipe culverts. And in the lower right-hand corner, you see headwater depth for corrugated metal pipe culverts with inlet control. So we're going to check inlet control headwater first, so we're going to use this chart. Using this nomograph, we're going to start from the left and work towards the right. So the first scale, or the first set of vertical lines that we come to, says diameter of the culvert in inches. And you see that right here is a spot 36 inches, and we're going to put a dot there since we're looking at two 36-inch corrugated steel pipes. So put a little dot right there at 36. You move over to the right, and the next line is discharge per barrel in CFS, and we said we have 46.5 CFS in each barrel. So I'm going to put a tick mark at right above 45, about right there. All right. Now the next thing we do is we need to then draw a line from our 36 inches through our 46.5 to one of these three lines over here on the right. So you'll see these three lines are labeled 1, 2, and 3. If you look at the key here that's in 2 font, and is also blurry, you will see that one go down here. One corresponds to a square edge head wall. Line 2 corresponds to an entrance condition mitered to conform to slope. 3 corresponds to a projecting entrance. And we know each one of those is different because of momentum. A projecting entrance is difficult for water to navigate because the water is being forced to make 90-degree turns into the barrel, so it's not hydraulically efficient. A square edge head wall is better as far as the efficiency, but it's still not the best. And we know that we have a square edge head wall, so we're going to use chart or the line number 1. Okay. If you actually had a projecting entrance, say line 3, then what you would do is you would connect your 36, you would draw a line through 46.5, and you would follow that all the way up to this line, and then you would come straight over, just like they did in the example, you would come straight over and read a value off of line 3. Since we're using line 1, we just have to connect the 2 dots and make a line to some place on line 3. So with a nice straight edge, and I usually for this will just use a sheet of paper, but if you have a straight edge or a ruler or something, that would be good to use. I'm going to start at 36. Put it through 46.5 and draw a line over here to line number 1, and I'm going to put a dot there. And you're going to read off a value that's somewhere, that line looks horrible. It's going to be, here's 1, here's 1.1, here's 1.2, and this is a logarithmic scale. So 1.1, 1.2, it's not quite 1.3 on line. What values are you getting? I hear a 125, 123, 125,
124.
Well, at least you stopped at 1.2 something and didn't go 1.2538 or something. So I guess that's something in itself. The value from the official answer key is 1.25, so let's just use that just so we're consistent and I can double check all our answers. All right. You notice what that value is actually what?
Headwater portion to the diameter of the pipe.
Yeah. It's headwater depth and diameter, so that's actually HW over D. All right. So we're going to put this in the HWD column on our sheet, which I've already misplaced. Here it is. So we're going to put 1.25 here. So what you did was you solved for HW over D, or the ratio of the headwater and inlet control to the rise of your culvert, or in this case, the diameter of the culvert. So if we actually wanted to just get the headwater, HW over D times D equals HW. So we need to multiply this value by 3 feet, and that will give us HW. Okay. HW over D times D equals HW. And if you do that, you come up with 3.75. Okay? So that value is actually our headwater depth right at the upstream side of our culvert and inlet control. And then if we actually wanted to translate that into our headwater elevation and inlet control, we would say, let's say space work. HWI elevation equals our elevation at the inlets invert of 247.23 plus 3.75 And that is some value. Oh, actually, I'm sorry. It's that column 4. We can put that right there. So what is that value if you do that calculation? It's 250.98. Is that correct?
Can you use that or 251?
Yeah. Honestly, yeah. You know what? If I'm reporting out these values, I probably, if I'm not working in a flood insurance study area where they probably more often than not require things to the 100, then I'm satisfied with 251. But just for sake of argument, we'll just say 250.98. And what that is what I calculated was a headwater depth. We need to check it against the allowable headwater elevation, so we need to put it in terms of elevation. So I just added that depth onto the elevation at the invert of the culvert at the upstream side, right? Transform it from depth to elevation. And that's 250.98. Is that okay?
Yes.
Because our allowable is what?
253.
253, we're at 251 for all intents and purposes. So inlet control works, but we don't know if it's inlet controlled or not because we haven't calculated the outlet control headwater. That's our next step. So outlet control, you notice when we did the inlet control calculation, did the barrel roughness and length and tailwater come into play? No, because we're simply solving the orifice and weir equations, right? All that other stuff doesn't matter. Now for outlet control, you're going to start seeing these other things come back into the picture because we're solving the energy equation from the inlet to the outlet. So the first thing it asks for is the tailwater, and we know that the tailwater is given as what? 2.57, right? From that stage discharge curve for the tailwater section?
Yes.
Right? That was provided. The tailwater depth is 2.57 feet. Is that what we're going to use for our tailwater? We don't know. Because remember, if we have a low tailwater condition, and that's, if we have a tailwater depth that's below that crown of the pipe, we have to make sure that that tailwater, well, let me just back up. We have to compare that tailwater depth to that d sub c plus d divided by 2, and then take the larger of those two. So we have to do the calculation of d sub c plus d divided by 2 and see if that's larger than the tailwater. So we need to find the critical depth in a circular shape flowing part full. Right? I want to go back and start smelling markers again when I hear that. So what we need to actually do is pull out a chart for that. So back in the day, if you had a question in hydraulics, they said, well, you know what, we got a chart for that. Nowadays we say, well, you know what, we have a software program for that. So back then they had charts. And so what we need to do is go to chart 4B. And on chart 4B, you see this. You see discharge on the x-axis, and then you see critical depth on the y-axis. And there's a series of these charts, and we need to find the one that seems like we could actually use it. The bottom one has really large discharges, and 1,000, 2,000, 3,000. That's way too much. We need something smaller. If we go all the way to the top, we see it's in increments of 10. You see 10, 20, 30. That seems like that's more of the ticket for us. We have a flow per barrel of 46.5 as we're looking at the critical depth in a barrel. So 46.5 is about right here. You go up to the line that reads 3 feet, 36 inches, right? So you go up to the line that reads 3 feet, and they kind of all get mashed together. And then you're going to go hit that line and then go directly over to the left and read off a value of critical depth. And you'll come up with so 46.5, go up to the line that says 3 feet, go directly across to the left, and you're going to read off a value of critical depth of about 2.2, 2.2, 2.2.
Yeah.
Does anyone get anything that's not in the vicinity of 2.2? Okay, we're all pretty comfortable using that figure. The answer key says 2.2, so let's use 2.2. All right. Since these, again, we're doing all of this because the nomograph that we're going to use next was based on full flow. It even says it on it, based on full flow. And if we have a really low tailwater, we're violating the assumption, so we have to make a little bit of a correction. And we're doing that by comparing the tailwater to d sub c plus d over 2. All right, so do that calculation, d sub c plus d over 2, and you'll come up with the value. That says, this chart here actually, it's hard for me to read. I just found out a few months ago that I needed to start using reading glasses. That top of that column there, it appears to me it says d sub c plus. Yeah, that's not correct. Scratch that h naught out. It's d, capital D. Put that capital D in there. That's confusing, and I don't know what else in there.
Because they have an equation for, yeah, okay.
But the way we're doing it is d sub c plus d over 2, and that's the second value to calculate, and that comes out to be, yeah, I think I heard you correctly.
2.6.
2.6 is what I got. All right. So, what's our H naught?
2.6.
It's 2.6 because the tailwater is 2.57. 2.6, they're both pretty close, but we're going to use 2.6. H supposed.
H sub O is supposed to be H sub O?
Sorry, question?
Not H sub O is supposed to be H sub O.
Yeah.
Okay.
H sub O is always the larger of the tailwater, or d sub c plus d divided by 2. So we're going to use 2.6 as, and you can consider that your new tailwater for all intents and purposes. It's a little fudge factor, so we can use the full flow nomograph. All right, K sub E. So remember back when we were talking about, we calculate in outlet control, we calculate the entrance loss by taking the K sub E value times the full barrel velocity head. A K sub E, do you remember what it might have been for a square inch head wall?
0.5.
0.5, exactly. So K sub E is 0.5, and again, you can look that up in HDS5 for all the different entrance shapes and types. Now we need to calculate H. Now what is H? Here's the figure that you should have in your worksheet that you'll see in HDS5. Here's H naught that we already calculated as 2.6, and we're going to determine H from the outlet control nomograph, which is the sum of all your head losses. It's that entrance loss, it's the friction loss through the barrel, and it's the exit loss. So the nomograph we're going to use actually calculates all the head losses for you in one capital H, just by using the nomographs. Pretty cool, huh? So that's what we're going to use. And that is going to be this chart, which is 6B. All right, so again, you see the circle in the upper right-hand corner, which means pipe culverts. This is the head for standard corrugated metal pipe culverts flowing full. We're not flowing full right at the end exit, but we made a little bit of an adjustment with our H sub O, so now we can use this nomograph. Okay. This one, we're going to start on the inside and work out. All right. So we're going to start with the two inner scales, what they're called, and work out. So here's the diameter one, and we're going to get a spot here for our 36-inch diameter and put a mark right there.
Why 36 and not the 2.6 feet that we calculated for the H naught?
Okay, so this is the diameter of the culvert.
Okay.
All right, this is the diameter of the culvert. So we put a 36 inches there, and then we have a choice of 3 curvy, succulent, delicious selections over here. So you see one is labeled as a case of B of 0.25, which would be pretty close to a bevel, and we don't have bevels on our head wall, so we're not going to use that one. We see a case of B of 0.9, which would be thin edge projecting condition. We don't have that, so we're not going to use that. The middle one is 0.5, which is the case of B, or the energy loss coefficient for a square inch head wall, and we're going to use that one. Okay? So we're concerned with this middle one, and we need to mark a spot on there that's right around our length of 150 feet. So let me see if I can do this. Here's 100. Here's 120. Here's 140 right here. And here's about 150 right there. Okay? So the next thing you're going to do is you're going to draw a line from that 36 inches that you marked on the diameter line, and you're going to draw it right up to this spot that we marked on this inner curvy line at 150 feet, or 149 feet. And once you do that, you're going to come up with a point on this straight line without any marks on it that's called the turning line. And so draw a line between the diameter line and this curvy line, and then mark a spot on the turning point. And not with this example, but the actual numbers you use. Mark a spot there, and that's the one that we're going to be concerned with. So I'll fudge it in here just so you kind of see the process. And so I came up with something that's right around there. Okay? Good so far? Found a nice big dot on your turning line. All those other two scales go away now. We don't care anymore. We've moved on. The next thing we do is we go all the way to the left to our discharge in CFS per barrel or per foot of width. But since this is pipe culvert and we're using that as per barrel, so that was the 46.5. So we put a line here at 46.5, and then we're going to connect that dot through our dot on our turning line, and we're going to carry it all the way over to the right to the one that says head loss. It says head in feet, that's head loss in feet. And you're going to come up with some magical number that hopefully is close to what I have on the solutions. And I think I heard someone say something that sounds reasonable.
4.2.
I heard 3.8, 3.2. 4.2 is probably too high.
3.6.
3.6. Once my eyebrows start to go up, and now you're getting really close. 3.9. 3.4.
Oh, yeah. 3.6.
So I hear 3.4 and 3.6. So let's just say 3.5 because that's what the solution says. So H is 3.5, and what is that again? What is H again? Capital H?
Total head loss.
You're getting it. It is the total head loss. It's the entrance loss, the friction loss, and the exit loss, all wrapped together in one number. So that's all your energy losses. We're solving the energy equation, so this gave you all your energy losses from the inlet to the outlet. So what do we need to do now? We go back to the figure that you should have here and say, well, we know this is that 246.48?
Yeah.
We add on H sub O, which is plus H, which is, and that becomes our headwater. That's our headwater elevation because we started with an elevation here. That's our headwater elevation for outlet control. And so do that calculation. What are we neglecting when we do this? Velocity head, right? I mean, in this case, we've neglected velocity head. We assumed it's close to zero up here. And we also kind of neglected it down here, which is not quite right. But it's an estimate, right? I mean, this is what they did back in the day. So what did you come up with for your headwater due to outlet control conditions? Actually, I had the answer up there. I scanned it.
49.98.
So it is 252.6. Who did not get that? $252.6. All right. So what do we now need to do? What do we compare that to?
Your allowable.
Maybe you're skipping one important step. You actually compare it. We're doing minimum performance. So we're going with the headwater that's the highest because we said that the conditions are kind of maybe possibly fluctuating between inlet control, outlet control, we're not always sure. So through minimum performance, we're going to take the higher between inlet control and outlet control and assume that's the way the culvert's operating for our design. So 252.6, 250.98, 252.6 winds, and that's our control headwater elevation, 252.6. Then we compare that to our allowable of 253, and we say it's less, right? And so we're good to go. And so that 252.6 is good. So you can say good to go.
Can't see what's wrong.
Are you done? No. What do you need to do next? Well, you do need to do the check flood, yes. For your design event, you still need to calculate the outlet losses.